Great. All right. Well, let's go ahead and get started. Thank you so much for joining us for day 2 of our Transforming the Global Power Sector, Open Tools and Data for Renewable Energy Integration webinar. My name is Holly Darrow. I'm a communications strategist at the National Renewable Energy Laboratory, or NREL, and I will be your moderator today. This training is brought to you by the Global Power System Transformation Consortium and the USAID-NREL Partnership. Before we get started, we have just a few notes about using Zoom. This webinar is being recorded and will be shared with you after it's finished, as well as the presentation deck. You are automatically muted upon joining and throughout the webinar, but please use the Q&A function in your toolbar to ask questions for our presenter, and we will address those questions during the Q&A portion at the end of the webinar. You can use the chat feature like you are now to introduce yourself, to add comments and share input. We do love to hear from you. If you have any technical issues, please use the chat feature to message Isabel McCann or me, Holly Darrow. You can adjust your audio through the audio settings. If you're having issues, you can also dial in and listen by phone, and that information can be found in your registration email. We did have a session yesterday, and to review the recordings and resources from yesterday's session, please visit the link on your screen, which Isabel will also put in the chat. That link also has the optional resources for today's side-by-side learning session. So today's agenda, our speaker, Dr. Kate Doubleday, is going to recap what we talked about yesterday, overview production cost modeling workflow and do a sample analysis, go over resource visualization and site screening using the Renewable Energy RE Data Explorer. She's going to do a production cost modeling demonstration in Sienna, as well as share some open source training resources before we have a Q&A and a wrap up. For those of you who didn't join us yesterday, Dr. Kate Doubleday is a model engineer and researcher in NREL's Grid Planning and Analysis Center. She has a PhD in electrical engineering and research experience in power system operation, renewable energy forecasting, and vehicle electrification. So with that, I'm going to hand it over to Kate to get started. Oh, apologies. It looks like Kate may have dropped off the call. Let us wait just a moment and we will get her back on. Hold, please. Okay, great. Kate has rejoined. Sorry, everyone, for the small interruption. Kate, we are ready to start whenever you are.
Hi, sorry about that, everyone. Just a little surprise technical difficulty first thing in the morning. So thanks for joining us again. Good morning, afternoon, evening, wherever you are. Let me get my screen share started. All right, hopefully folks can see slides now. Holly,
Yep, we can see.
Great. Okay, then let's go ahead and get started. So thank you again for joining. Hopefully folks are able to see the introduction webinar yesterday. If not, we just want to give a quick little recap of some of the key topics that we talked about. So we talked about the need for flexibility in the power grid in order to accommodate very high proportions of VRE, or variable renewable energy. So there are various types of flexibility, from new data and markets and storage. So production cost modeling, which is one of the focuses of today's demonstration, is a simulation tool that we can use to model most or all of these flexibility options that gives us the ability to compare, contrast different ways of adding flexibility to the grid. So there we go. So we talked a bit about the unit commitment and economic dispatch, two stages in a classic production cost model, which are operational simulations that are trying to minimize the operating cost of the system over the next day. We typically use a 48-hour horizon, including the day of interest, as well as a 24-hour look ahead to make sure we're capturing sort of the medium-term behavior of some of our slow-moving generators and we don't have edge effects. We can step this type of simulation forward day by day over the course of a year to get this time-varying simulation of power system operations. Within each day, we can then feed the outputs of the day-ahead unit commitment into a finer resolution, intra-hourly, typical 5 or 15-minute economic dispatch model to understand how our day-ahead decisions impact things closer to real time. So this type of simulation can be used both operationally by system operators, as well as in a planning context for us to compare and contrast different options. This type of production cost model is an optimization problem. So it's structured as a set of mathematical equations with an objective function that we're trying to minimize. We're trying to minimize the operating cost subject to the realistic constraints of the system. So we can write this as a mathematical program, write this in a mathematical program like JUMP in the Julia language, which is what we'll be using in the demonstration today, and then solve it with a proprietary or open source solver. There are several open source options in order to find that minimum operating cost point. We also talked a little bit about some data resources available for this time varying simulation. So my colleague Galen introduced two important data sets that are available, particularly in the Southeast Asia region. So we're celebrating the release of a new wind resource data set for Southeast Asia that includes the years 2007 to 2021. And this complements an existing data set released in February 2021 of 10 years of high spatial and temporal resolution solar resource data. So we can use both of these time-varying data sets as inputs to a production cost model, and that's what we'll show today. So here are a couple of the key takeaways that we talked about yesterday. We talked about this, again, this idea of flexibility and adding flexibility to the system in order to increase the proportion of variable renewable energy that we can confidently use. We talked about comparing and contrasting options for operational flexibility using production cost modeling. We talked about the different users who might be interested in production cost modeling. That includes system operators who use production cost models in a daily, hourly, and sub-hourly basis to run their operations, but also use PCM in a planning context. So both system operators and policymakers might be interested in that type of workflow. We also talked about VRE plant developers who could use production cost models during the site feasibility stage of their project development in order to understand the impacts of the grid operations on plant operations. So that could include looking at issues like transmission constrained curtailment. It could also be used to compare different operational or market bidding strategies, which is particularly useful if storage is involved, or potentially if a VRE plant is bidding into multiple markets like ancillary service as well as energy markets. And our hope is that these open source data and tools can reduce the cost and difficulty of doing this type of site pre-feasibility and feasibility study. So those were the main takeaways from yesterday. Now we want to introduce the demonstration workflow that we'll be going through today. So this involves 3 open source tools: the RE Data Explorer, the System Advisor Model, SAM, and our production cost modeling tool, Sienna Ops. This workflow is a little more similar to how a plant developer might use a production cost model. And that's just because we're going to be doing our early sort of site prospecting in the RE Data Explorer to pick a handful of sites that we might potentially develop. This is just in contrast with how a system operator might use a production cost model as the second stage after doing a capacity expansion model to plan for their needs in the future years or decades. So we will use the RE Explorer mainly as a resource for downloading this high fidelity wind and solar resource data that we were just referring to, that we can use as inputs for the rest of our modeling steps. By combining that high fidelity time varying resource data with some standard plant specifications and plant loss assumptions, we can use the System Advisor Model, SAM, to model the electricity production profile from a hypothetical plant at that location. In addition, SAM has various financial modeling capabilities. By combining this electricity production profile with some information about the cost, compensation, financing, and incentives, SAM can also provide various financial feasibility metrics that might be of interest, including levelized cost of energy, net present value, and payback period. So this information can also be useful in the site feasibility stage of a project development. But for this demonstration workflow, the output that we're really interested in is this electricity production profile. Once we have the maximum electricity production available for each plant, we can use that as an input into our production cost model, combined with information about the existing thermal generators in the system, transmission constraints, and the demand time series. And that can provide us with classic production cost modeling outputs, including locational marginal prices, transmission line flows, curtailment, as well as the overall operating cost. So this is the flow that we're going to follow today. And our sample analysis is conducted on an open source set of data available on GitHub for Cambodia. This is an hourly resolution operational model that includes time varying demand, as well as a set of hydro generators and thermal generators, but it does not yet include any wind or solar plants. And so what we'll do is we'll select a handful of hypothetical locations to add wind and solar plants to nodes in this existing transmission system. And that will enable us to do a little before and after comparison in our production cost model. So if you haven't had a chance already and you're interested in following along either now or with the webinar recording, this is the link for the case study Git repository. I think that'll also be included in the chat. We do want to come to present a couple of disclaimers before we get started. This case study is for illustrative purposes only. We are not endorsing any specific brands or technologies or developing specific or endorsing the development of specific renewable resource locations. We're going to do a very preliminary site prospecting in the RE Data Explorer, but we did not include any practical due diligence about renewable energy siting, including if there's even enough land at the locations we choose to build the quantity of capacity that we assume. So just use it as an illustrative example. And we also did not consult or get endorsements from any local experts or authorities. So please keep that in mind. And now we'll move into the first step, resource visualization and site screening with the RE Data Explorer. So Galen introduced the RE Data Explorer a little bit yesterday, but just to reiterate, this is a geospatial analysis tool that you can access anywhere online. It includes a variety of different informational layers that can be useful in early stage prospecting. And it can also be used as a repository to download these high quality, high resolution wind and solar data sets. Wrong direction. Okay. We specifically want to call out the availability of wind and solar resource data in the Southeast Asia area, including this new wind data set that is just becoming available. The RE Data Explorer also includes a couple of analysis tools that can be useful. That includes a technical potential calculation. So technical potential includes considerations of the available area, power density, and mean capacity factor at that location for a wind plant or PV plant over the course of the year. It does not include any market feasibility or financial data yet, but it can be used in the early stage to compare locations that have the capacity to produce the most energy. There's also a levelized cost of energy analysis tool. So this is a standard financial metric that takes into account the capital expenditures and operating expenditures, in addition to that potential annual energy production. So this is a simple way of comparing across different generating technologies. And so this is also a way that we can visually compare and contrast the financial feasibility of developing different locations. We also want to give a brief discussion about how to select data from the RE Data Explorer for use in production cost modeling. When we talk about production cost modeling, we are looking for time coincident demand, solar, wind, and hydro data where available. Hydro data is often can be scarce and hard to find. Particularly if you're coming from the solar development world, you might be familiar with the idea of typical meteorological year weather data, or TMY weather data, which is popular for calculating the expected performance of a solar plant. So that is calculated on a location by location basis. It is appropriate for use when considering a single RE plant in isolation. But when we get to these system-wide studies, like production cost modeling, it's not an appropriate usage because we don't have that guarantee that all our time series data is time coincident across locations. And so if we aren't consistent in our weather modeling, we can't capture the full impacts of weather on the electric grid. It has an averaging effect, and we miss out on some of those stressed periods during the year, and also extreme weather conditions, which are becoming more and more critical as we look at electric grid reliability. So our recommendations when selecting time series data is to base our production cost models on actual meteorological year, AMY weather, consistent across all of our data sets. There are also some options if we're modeling historical forecasts for modeling those from a consistent source, again, so that the model is consistent across different technologies and demand. So since the case study that we're basing our production cost model on was based in 2016, we will use 2016 AMY solar and wind data from the RE Data Explorer to match that. And so we have a time coincident system. And now we're going to move into the demonstration. So let me go ahead and move over to the RE Data Explorer. Okay. So I am here at re-explorer.org. once you're at the landing page, you can access the Data Explorer directly from the top menu. I already have a data layer calculated here, but if I was approaching this for the first time, the first place I would go is to the data library in the left-hand toolbar. And I would get a sense of what the land use and existing infrastructure looks like in the region of interest. So once you're in the data library, there are a variety of categories that you can select from. And I'm going to select the environmental land use category, as well as the grid category. And I think maybe the environmental category as well. So the first thing I'm going to look at is I'm going to understand Cambodia's existing land use. So we have a mix of wildlands and forests, as well as a large agricultural area in the center, and this large body of water as well. We can overlay that with protected areas. So that's often useful for understanding exclusions where new infrastructure likely can't be built. And so we won't include these in our analysis. The other thing that's useful to see is Cambodia's transmission lines. So where is it existing infrastructure and where would be most useful for us to locate? It's most useful for us to locate close to these transmission lines and nodes so that we don't have extensive costs for interconnecting far from these transmission lines. The other thing I'll look at is the global power plant database. So this gives us a sense of the existing infrastructure. This is similar to the slide we just saw about the PowerNet system, where we have a set of hydro generators along the coast, as well as some fossil fuel generators. So with that, I'm interested in potentially looking at building some wind and solar plants in this area. The next thing I'm going to do is look at the available resource. So I will demonstrate this for wind, but a similar thing could be done for solar. So I look at the wind resource. Oh, there are my layers. Let me take that off. And there are a variety of available at different hub heights and from a couple of different resources. So it would be useful to click through those various layers, but I'm just going to look right now at the 100-meter wind speed. And I'm wondering if, I don't know if folks are seeing that. Let me move that out of the way. It's in my way. Okay. So when we look at the wind speed, this is in units of meters per second. And generally we're looking for higher resource, which will be have a higher output. So I can see right away that there are some locations down here on the southern coast, which are have higher resource than other regions. And so this is probably a region that I would be interested in looking into more. So now let's take a look at one of these technical potential studies. So I have previously loaded one of these studies. Let's see if that can show back up. Great. But if I was approaching this for the first time, I'm going to put on the transmission lines as well. I would go to this technical potential bar on the left and click through a series of questions. Back. So I have this new technical potential layer I've selected for Cambodia. You can select certain regions. I've selected the entire country. I've selected wind resource as opposed to solar. So again, you can do the same thing for both. And for wind, it asks me about technology type. And so this is where it has been useful to look at the wind resource availability before I get to this stage. So there are some recommendations here about the standard example turbines that are most productive at different wind speeds. And so based on the wind speeds that we saw in the resource, I think either the T200 or T237 might be reasonable options. Again, it would be useful to do this with both, but I'm going to select the T200 for this case. I click next. There are some additional parameters that you can refine with some standards provided for your ease. And all I did was I added a limit distance to transmission to 10 kilometers. And I did that just because, again, we don't want to be potentially building out where we would need a very long transmission line extension. I click next, and then we can exclude some certain areas, including the protected areas, as well as certain land types. So I've removed urban and water, wetlands, ice, which is a bit more of a relaxed scenario, and run the analysis. So that's what's showing here. And what I'm seeing is consistent kind of with what we saw with the resource. So the areas with the highest technical potential are aggregated down here around the southern coast. And in order to do one last check that this is a region that's a good choice for us to add some wind plants, we could also do a levelized cost of energy analysis. So this is very similar to the technical potential process. Let me go back here. We start by selecting our region, select the currency, the resource type, and in this case, we can choose a potential scenario from a couple of different options that have different assumptions. So I've chosen a relaxed scenario. Again, it could be useful to do a little comparison there. There are some assumed default country values. I haven't bothered changing these. So all we did is click through and hit run analysis. Now, I believe that for whatever reason, this one is not showing up for me this morning. So I'm going to switch back to screenshots. So this is the output of that type of levelized cost of energy analysis that I conducted in the past. So in this case, we're looking for a low levelized cost of energy, and we see again that the southern region is in the lowest range, and that's what we're looking for. So based on this very preliminary analysis, we didn't do any additional site screening besides that, but we're going to pick a couple of locations to add hypothetical wind plants. So for demonstration purposes, we picked 2 locations near existing nodes in the transmission system. And those are where we'll go ahead and download high fidelity resource data and model those in our production cost model. Now, I'm not going to demonstrate this in the tool, but we can do a similar thing with solar. We can review the solar resource. We see that the middle of the country in this case has higher resource and will be more profitable for us to look in those regions. The technical potential study with a fixed tilt system confirms that, and so does the levelized cost of energy analysis. So from there, we've picked 3 different nodes where we'll interconnect hypothetical solar plants into our existing transmission system. I'm now going to return to the RE Data Explorer. And I just want to verify that folks can see this whole screen. So I'm just going to stop share and reshare. Sorry for the technical difficulties today. Okay, there we go. So after I've chosen my locations, the last thing I can do in the RE Data Explorer is come to download. In this case, I'm going to download large scale data. So this provides access again to the Himawari solar data and the other data sets as well. And this needs to be sent via email. So you'll provide your email address, select the layer you're interested in. So in this case, for the production cost modeling, you don't need to actually go through this data download step in order to follow through the production cost model, because we have already downloaded 5 resource files for you and included them in the GitHub. But for demonstration purposes, if you'd like to add more, the 2 data sets that we have used are the new Southeast Asia wind data set, as well as the Himawari solar data set. And again, we're picking the solar data, the Himawari solar data as opposed to the Himawari TMY solar data, because this first data set gives us access to actual meteorological year historical data. So I'm going to click through on the Southeast Asia. wind data. It's giving us a demonstration of the region that is covered by this data set. And we've already picked some latitude and longitudes based on the proximity to transmission lines. But for demonstration purposes, I could query a location, click through to select the resource data I'm interested in. I find it's easiest just to select all, select the year we're interested in. So again, this data set has 2007 to 2021. I'm going to pick 2016 for consistency with the PowNet open source data set at a 60-minute resolution. And again, that is consistent with the existing data set as well. Finally, it's important to have a couple of considerations about time zone and leap day. These can cause issues when you have mistakes in the time alignment among data sets if they're not in the same time zone. So all of my data sets are in local time. So I'm going to choose local time, but skip leap day because it's not included in the additional data set. And then you can click download. It will send a link to your email. And from there, you can download a CSV file. Okay, so that concludes our demonstration of doing some data download and early site prospecting in the RE Data Explorer. I will now move to the next stage of the demonstration, which is processing these resource files in the system advisor model and then using those in a production cost model. So I'm gonna go a little quicker through this section. At this point, we do need to do some sort of file management. And so I'll show you a couple of the options available for processing these files and moving them, attaching them to the production cost model. So this is the case study Git repository. First thing to note and orient ourselves is that there's an extensive README at the bottom, which goes through many of these steps with links and more detail. So if you're interested particularly in processing the additional sites to add to this case study or doing this on your own case study, I'd refer you to this middle section about the system advisor processing. But if I open this on my local machine, the first thing I want to look at is this RE resource data subfolder. So in this subfolder, I've collected the input data that I downloaded from the RE Data Explorer in the solar and wind subfolders, just to give you a sense of what these resource files look like. If I open one up, it has some metadata about the location I've downloaded, as well as this hourly resolution weather time series. And so this is what we want to process into an estimate of electricity production. So there's a couple ways of doing that. I'm going to now open the SAM GUI. And if you are doing site-by-site modeling, the GUI is the most accessible way of doing this type of modeling. There are also programmatic options, which I'll talk through in a second, but that's only really useful if you have a series of batch files. So I'm going to demonstrate this now for a solar site. When I open SAM, I have this series of technologies that I can model. I'm going to choose the simple PV watts photovoltaic model. And it now gives me an options for the financial model I want to attach. There are distributed models as well as PPA models. But since I'm most interested in the electricity production profile for production cost modeling, I'm just going to use no financial model. And I'm going to click OK. It now gives me a variety of pages for me to design my power plant. So I'm going to go through this kind of quickly, but there are many resources on SAM available. I already have my local location for where I've downloaded these files added as a folder. So I'm going to find one of those files here, and I've now attached the resource file from the RE Data Explorer into SAM. I'm not going to change any of the system design parameters. I'm just going to assume this is a standard utility scale system, but this is where you can put in whatever additional information you have about the specifications you're looking at. I'm going to hit simulate. And just like that, we have an electricity production profile. I can look at it under time series. So here it is, system power generated in kilowatts. And if I want to export this for use in other models, we can go to data tables and save as CSV. Simple as that. So if we're doing this one by one, it could be a bit cumbersome if we're starting to look at a fleet of different options, or if we have a very large plant and we want to do some averaging of the resource data over that location. If we have multiple files for that location as opposed to just a single point, what we can do is use a Python wrapper around PV watts called PySam. So to model the same plant specifications over multiple weather files, an easy way to do that is to come to this project down arrow and select generate code. And from here, we can export a PySam JSON that describes this plant specifications. So you can click OK and download that code. I'm going to close SAM now and come back to the case study repository. So if I look in one of these solar or wind subfolders, you'll see that we already have some JSON saved. So these are some examples that we've already downloaded, just like I showed you in SAM. There is some code available in the RE resource data folder to run the series of plants with the same configurations through PySam. I want to point out one other file, which is this RE plant config file that includes some simple metadata about each of the plants that we are modeling. This is a sort of a manual hack that I created. It is not like a standard part of any of the models that we're looking at, but this is the way that I have attached our 3 PV plants and 2 wind plants consistently, both in SAM by indicating the resource file and the specification file that I want to use for modeling the electricity production, as well as the node acronym for where I'm attaching that in the PowNet network. So if you want to add to this case study, this is a file that you can adjust in order to use the existing code and have everything be automatic. So if I come back here, we'll just take a quick look at the text of this RE time series prep file. So if you do want to take the programmatic approach, which again, you don't need to, if you just have a handful of sites, you can download the CSVs through the SAM GUI. But if you want to model a fleet, you'll see here we have this code with using the PySam wrappers that uses that plant config CSV file to cycle through, use the same specifications on multiple locations to export a consistent wind and power CSV file. So if I look in the output folder here, you'll see that the sum total of that whole process is this CSV with an electricity production profile for each of our 5 plants. Okay, so now I'm going to move into the meat of the production cost modeling demonstration. We have our inputs ready. So I'm going to show how to set up this demonstration for the first time. In the bottom of the README, you'll see a couple of commands that we need to run the very first time that you use this Git repository. So I have navigated to this folder on my command line. I'm going to activate Julia, which is the programming language where Sienna Ops is written in. The backwards facing square bracket gives me the package manager for Julia. And if I say activate this environment that comes with the Git repository, all the packages necessary to run this code will be activated. The first time you run this might take a while. So go ahead and get that started if you're following along. The next thing I'll do is I'm going to hit backspace to get out of the package manager and run the second command, include literate.jl. And this is just a little helpful command that will process the Julia scripts included in the Git repository into Jupyter notebooks if you're interested in running them interactively. So once that has run, just to orient you a little more into what's available in this Git repository, there are two pieces of Julia code included, a Cambodia data prep script. This is automatically run when you use that literate.jl command. And this is just setting up the system. It includes attaching the time series data that we have just created, that wind and solar power time series, to the existing PowerNet system. So that's still running. The second piece of code that we're going to move into in a moment is the PSI Cambodia.jl script. And so I'm going to run this interactively in a Jupyter notebook. But this is the meat of the production cost model. So let's see if that's still going. I'm just going to open another terminal. So I've navigated to the folder. Actually, I'll go back to this one. Okay, so I've run my two preliminary scripts. I'm going to exit Julia and run Jupyter notebooks. Okay, so now that I have run literate.jl, I have two versions of each of the Julia files. The Julia script, which you can run in one go, and then this interactive Jupyter notebook. So let me open this Jupyter notebook. I'm going to use an extension that puts this in presentation mode. And we'll go ahead and get started with the production cost modeling demonstration. So the first thing that we'll do is we'll load dependencies. So if you were in the webinar yesterday, we talked about the key Julia packages used in each of the 3 core Sienna applications. So the Sienna Ops application, which we're currently using, uses a set of these packages, including power systems, power simulations, power analytics, and power graphics. Power graphics can be used to do some modeling of the production cost modeling dispatch stacks at the end of our processing. Another thing to note here is that we are using an open source optimization solver called HISE. So this is available open source. The other thing we're doing is using an interactive Plotly.js graphing background. If you have issues with this, I believe there is an additional download you might need to add. You can comment out that line. Okay, so the next thing that we're going to do is load in the system that we built with that Cambodia data prep.jl script, which was run through the literate command. So once this loads, we'll be able to see some metadata about this system. As that's loading, I do want to note that you'll see that the timestamps listed for this system are from 2017. And given that we just talked so much about time coincident data, I don't want that to confuse folks. That's just a hack we did because 2016 is technically a leap year and we didn't have leap day data. So the underlying data is all 2016. So let's take a look. We have some basic information about the system. This is a 30-bus system with 7 hydro generators, 15 loads, 5 renewable generators, so those are the 5 wind and solar plants we just added, and 20 thermal generators. We also see that some of these components have time series attached to our renewable generators, as well as the existing time series that was available from PowerNet for the hydro and load components. This is a 60-minute resolution system that has data for the entire year of 2016. And when we run this simulation, we'll be set up to do it with a 48-hour horizon, which includes that 24-hour look ahead. And we'll be able to do that 364 times because of the last day of the year. We don't have a look ahead into the first day of the next year. So let's continue on. Now we're going to set up a production cost model. Sienna Ops comes with a variety of template production cost models that make it straightforward to set up a standard unit commitment or economic dispatch problem. In this case, we're just setting up a one-stage production cost model using the unit commitment, and that's because we just have one set of time series data. So this template has a set of mathematical formulations that describe the operations of our various device types. So our thermal generators will use a basic unit commitment formulation that includes on, off, startup, shutdown variables. Our renewable dispatch devices will have a formulation that allows them to be curtailed if need be. That's in contrast with a renewable fix device type, which cannot be curtailed. So that can be useful if you're doing behind the meter modeling. But I'll note that we don't actually have renewable fix or some of these other devices in our model. This is just the template that can be used for a variety of models. And so it is broader and more flexible in that way. It also includes reserves for variable up and down reserves, but we don't have those in this model either. Now we're going to combine those two things. So we're going to apply the template to our data model. We'll also note again here that this is only a single stage model because we only have the necessary time series data for the unit commitment. So we don't have an emulator model specified. We don't have an economic dispatch or an AGC model following that. All right, so now I'm going to set up the simulation sequence. So this is describing how the information flows from one problem to the next problem. Since we're going to do this in a sequence of day-by-day steps, this describes how the end of one simulation feeds into the starting conditions for the next simulation. Now I'm going to define and build the simulation. So in this case, I'm only going to run 3 steps. So that means I'm going to run 3 days of a production cost model. We have the data to run a whole year, but it is a bit time consuming. That would take about an hour. So for this demonstration, I'm just going to show 3 days. If you're interested in running the whole annual simulation, I would suggest changing this value to 364 because of that look ahead, and also changing the simulation folder so that it saves the results. This is just going to use a temporary folder and delete it. So there's some additional examples of this type of simulation setup in the powersystems.jl documentation. And so I would suggest taking a look at that if you want to do any of these adjustments. All right, so after I've defined the simulation, it is going to build the simulation, and that means getting all of the equations ready for us to do the execution. This also includes some, warnings. We don't have certain components in this model. That's not a concern, but there might be other information here that you might be interested in double checking and verifying. So finally, we are going to execute. So now the model or the program is taking our 3 sequential steps day by day and running through those through the highs optimizer in order to determine the minimum operating cost for that day. And it will also, in the process, do a little back calculation to estimate the locational marginal prices at each time step and at each node. So again, this can take a little bit of time. Hopefully this will just take a couple minutes. If you are interested in doing annual simulations, I would suggest running this from the script. So going to a command line and running Julia and then the PSI Cambodia.jl. And that way it will you won't have to just have it in this interactive mode sitting here. And it should also give you a progress bar if you run this from the command line. All right, so it has finished our 3 days, tells us that the run was successful. We're looking for that 0 here. It also tells us some basic information about the run that might be of interest, how much time and the allocations that it required. So now let's explore the results. I'm going to start by loading the results from the simulation. So in a multi-stage simulation, we would need to access the decision problem results for each stage. Since I just have a unit commitment here, I just have one set of results to load. We can look again at some basic metadata about this simulation. Again, it only had 3 days that we considered out of the, that we have the data to run the whole year. This also describes some of the variables that we defined and some of the parameters that we used. So this problem was using this set of variables as decision variables in the optimization problem. That includes the line flows, whether the thermal generators were on, starting up, shutting down, and what their set point was. The other thing you'll note here is that there's no mention of renewable generators, and that's because I've actually set up this simulation to give us the base case first. So I'm sorry I didn't mention that before. When I loaded in the system, I have the renewable generators deactivated. So we'll first look at the results of this base case, then we'll add in the renewable generators and see how it changes. All right, so let's go ahead and plot the dispatch stack for this base case, again, with the existing PowerNet system, no renewable generation yet. This is using the Plotly.js backend, and so that is an interactive plotting approach. If you have issues with that, you can remove that call and it should produce a static graph that's, I think, the default. So here's our 3 days. We see the time varying load profile. We currently are just using hydropower, petroleum, and coal. We see that the assumptions in this model are that coal is ramping up and down in order to adjust for the variance in load. That's based on whatever parameters were included in the PowerNet system to describe the coal constraints for this system. So again, this plotting is interactive. We could zoom in, which is very useful if you're plotting, say, a whole year. You can zoom into certain days. Let's look at some other summary information. So I'm going to read the optimizer stats from this, the results. And this could be useful if you're just doing some debugging. It gives you some basic information about the status of the primal and dual variables, solve time. So just some basic information if you're interested in looking into any issues that you might have had during the solve process. Now I'm going to read in the realized cost for each thermal generator at each time step. The reason that we emphasize realized here is the fact that when we did this step-by-step simulation, we included that 24-hour look ahead. And so in this case, we've scraped out the look ahead from each window so that we just have the values that were kept from each 24-hour period sequentially. So we also did not include wind, solar, or hydro when I looked up these realized production costs, and that's just because in this problem, those have 0 operating costs, and so they don't contribute to the overall cost. So once I have these operating costs, I can then find the total cost of the system by summing over that table. So here we have the total operating cost for this 3-day window in the base case, and we can use that as a point of comparison when we get to the renewable scenario. Last thing we'll do here is look up a table of locational marginal prices. So these are estimates because this was a mixed integer problem. They're also represented here as reversed in sign, so these could be thought of as positive numbers. I have the locational margin price for each time step and each node acronym. It has a separate column. And one thing we'll note here is that we're seeing consistent prices across the nodes in the system, at least for this snapshot here. And so that's indicating that transmission congestion is probably not an issue, but that would be something to look at as well. So those are some of the summary stats that we can look at once we've run the production cost model. We could also do some other post-processing by, for example, using estimates of emissions to estimate the total emissions from our thermal generators now that we have their set points, and look more into the transmission line flows if we do have congestion issues. So now let's connect those thermal generators. All I've done here is looked up the 5 renewable dispatch generators and set them as available. This set available, set unavailable function is a handy way of adding or subtracting different components from the system, which can be useful for this type of comparative analysis. Because I have changed the system and what components are in the system, we've needed to rebuild and re-execute the simulation. So I've done all of that in 3 steps: build, execute, and look up the results. If you are interested in running the annual simulation, this might be a place to rerun the simulation definition just before this, including the 364-day step, and assigning a different folder location so that you can have your renewable and your non-renewable results in different folders. And I might update the GitHub with those suggestions, but they're not currently there. Okay, so it looks like this has successfully built and run. So let's take a look at how this dispatch stack is different. In addition to the 3 types of generators we had before, we now have some wind and solar as well. The quantities here, again, are just based on the sort of arbitrary plant capacities that I picked when we were adding these, when we were simulating these plants in SAM. We could go through that same set of post-processing we did with the base case, but in this case, I'm just going to do a quick little sum of the overall operating costs, which could give us a point of comparison to the number we saw before, which I think was 94 something. So as we'd expect, since we now have plants with 0 operating cost in the system, our total operating cost goes down. So this concludes our demonstration of Sienna Ops. If you're interested in more information, I would suggest that you look at some of the documentation links that I'll share in a moment, which have other examples for ways of setting up the simulations and post-processing the results. So let's go back to our wrap up. I'm going to switch back to the slides. So some of the key takeaways from today are that the new Southeast Asia dataset provides a high-resolution open source dataset that we can use as inputs to this type of production cost model, both for site pre-feasibility and feasibility studies. And this complements the existing high-resolution Himawari solar dataset that was available for this as well as other regions. We're hoping that this type of open source data and tools can help reduce the cost and difficulty of conducting planning and feasibility studies. And we can use this type of production cost model to understand different flexibility options and do sort of before and after comparisons of different scenarios. By increasing system flexibility, we can use higher and higher proportions of VRE, and that's the goal of some of these tools that have been specifically built to do high resolution detailed modeling of wind and solar resources. For more information, there is plenty of help resources on the RE Data Explorer website, as well as the SAM website. SAM has an extensive set of resources as well, including a support forum for questions. You can also see what questions other folks have asked. There's a YouTube channel with more demonstration videos. The SAM team also makes itself available for bi-monthly roundtable sessions where you can ask questions to them directly. And there's also an email support line. For Sienna, I would recommend that you first take a look at the package documentation for each of the 4 packages listed here, which includes the dynamics packages if you're interested in Sienna Dyne. These packages documentation also include quick start guides and tutorials. So there's more code there for setting up sequential simulations, including a unit commitment to economic dispatch feed forward, as well as other types of formulations. There's a Slack channel that you can join for discussion with the Sienna team, as well as updates as the packages continue to evolve. And the Sienna NREL team can also be reached at this email address. So with that, thank you so much for your time. That concludes our demonstration, and I'll hand it back to Holly for the Q&A.
Thanks, Kate. That was so detailed, and I know a lot of people really appreciate like the in-depth walkthrough. So thank you so much for that. We have quite a few questions, so we'll kind of get started. Anything that you feel like you can't answer related to RE Data Explorer? For the participants, our RE Data Explorer researcher Galen is out today, and so any questions that Kate can't answer related to that application will direct to Galen, and then post on the event webpage, the same place that you found the GitHub resources and the recording of yesterday's session. So to start it off, we do have a quick question about if the data from RE Data Explorer can be integrated with Python. Do you happen to know that, Kate?
So I will take a stab. So first of all, I believe there is also an API for accessing data through the RE Data Explorer. Once you have a file in any of the CSV formats that come through the RE Data Explorer, that should be very easy to integrate into Python. So I don't have an example of that, but Python absolutely has the ability to ingest those files.
Okay, awesome. And then the API, that's related to, like, we have a question about if it's possible to download the research data from RE Data Explorer programmatically so that it can all be automated. Is that related to that question?
That is related to that question. So I showed a manual download. I don't have a demonstration of using the API. I believe there is one. So this is a question to verify with Galen, or I'm not sure if there's information about that on the RE Data Explorer website.
Great. Yeah, Ben, if you wanna peruse re-explorer.org, there might be an answer to it there, and we will ask Galen as well. Great. Okay, so can you comment on the use of historical plant generation in these modeling efforts instead of using meteorological data and a generation simulation, pros and cons, for example, how to deal with generator outages embedded in historical generation data?
So I think the question is asking, if I have a recording from a power plant of what its generation was historically, how can I use that versus doing a 2-step model where I first use a meteorological data and then a simulator like SAM? Okay. So actual measurements are always better when they're available. So if the data set is complete, that's a great use of historical plant data. One issue that I have seen in historical measurement data is that depending on the plant, there can be measurement outages very regularly. And so the data set can sometimes be not as complete, and that might not be like due to a plant outage, but a measurement issue. So that's just something to keep in mind. But if you do have a complete data set that includes the outage data accurately, absolutely, that's a great use in a production cost model.
Awesome. Also related to data, and I know you mentioned this a little bit during your presentation, with regards to leap days, do you advise ignoring data from the leap day and having a disconnect, or ignoring data from either the first or the last day of the year to avoid that type of disconnect?
That's a great question. It's a common problem. All I advise is consistency. So if you have a data set that doesn't include leap day, take it out of all the other data sets, and you will have a disconnect from the 28th to the 1st. But in the span of sort of stressed periods during the year that you're trying to identify with the production cost model, it's probably not one of them. So it can be fine to try to just remove it. And then it is pretty common to have some sort of incomplete data set at the beginning or end of the year. Like in this case, if we wanted to run this model, we wouldn't be able to run the last day without a feed forward. One of the options is to just reuse the first day of the year. So reuse January 1st, 2016 as January 1st, 2017. But again, it comes down to sort of the marginal value of, if December 31st probably wasn't your most stressed day, maybe you don't simulate it.
Right. Okay, awesome. And then we have had like a couple of questions, and I know we talked briefly about this yesterday about using this model for price discovery. Can you like identify the electricity marginal price for an additional power plant? Can you model future pricing for, you know, days coming, that type of modeling?
So locational marginal prices are one of the outputs of a production cost model when you have a nodal representation of the transmission system. So you need to have, you know, information about the power lines in order to be able to figure out the locational marginal prices. They are estimates depending on what type of optimization model you are using. And they're also only as good as your forecasts. So we talked about this a little bit yesterday. You can use this type of day ahead model to give an estimate of locational marginal prices. But if your demand, solar and wind forecasts are significantly off, or if there are other unexpected occurrences, those won't be captured in your estimates of the next day's prices. And so again, I would recommend that you consider a set of sensitivities or scenarios around the inputs to understand a bit of the uncertainty in the prices as the outputs. As we go farther into the future, not just the day ahead, but if you're looking long term, again, the uncertainty in fuel prices just gets higher. And so that's something to keep in mind, the importance of considering the uncertainty around those forecasts.
Yeah, absolutely. And then like on a smaller scale, is it possible to run this model for a residential system or an off-grid system to get the same like kinds of outputs or same kinds of analyses?
That's a great question. So for a residential system, really all you would need is PV watts in SAM. So you could download some data from the RE Data Explorer and simulate it in SAM using like a distributed, one of the distributed financial models, if you'd like. There's also like a residential and a standard default residential size in PV watts. And so that would give you all the output that you need to understand what an individual house is doing. If you're talking about microgrid, I believe there are other microgrid simulators out there. We did not include specific microgrid simulator links, I think, in the links yesterday, but there are certainly options.
Awesome. And then I think this is, more of a question that's again kind of behind RE Data Explorer, but again, if you know, feel free to answer, and if not, we'll direct to Galen. Do you know about the resources behind transmissions lines for, that data set that's used in Cambodia? And if not, like, for example, where did this grid data come from? Just wondering if you are aware.
That's a great question. So to answer this more generally, let me see if I can just pull it up right now. One of the useful things about the RE Data Explorer is that you can query the source of any data set. So if I go, let me just screen share really fast.
Yeah, if you want to share your screen and show, that would be great.
Okay, so if I pull up the Cambodia transmission line data set, let's see, you'll see this down arrow, and it will tell you its source, as well as links. So all that information is available.
Awesome. Yeah, that's great that everyone can kind of, see where it's from and kind of investigate that way. Can you do this type of modeling for example, like biomass, electric energy, or other sources of renewable energy generation?
Yes. So SAM has a variety of technologies available to model, not just wind and solar. I believe biomass is also in there, fuel cells, solar heating, marine energy, and tidal energy. So all of those technologies can be modeled with SAM, again, assuming that you have some reasonable inputs about the specific system you're looking at.
Yeah. And then like for this type of modeling, is there a way to include a time series of demand on the grid for modeling the grid? For example, like if everyone turns on their AC when it's hot or their heat when it's cold.
Yes. So if you recall those dispatch stacks that we showed at the end of the production cost model, let me pull that up real fast. Let's see. I should just leave screen share on. Oops. Sorry. Okay, so this type of dispatch stack here, the black line at the top is that time varying demand. And so it's actually one of the most crucial inputs for a production cost model is to have that time varying profile for demand. In this system, I believe we had 15 different nodes that had demand profiles. So this is the sort of the system total, the sum of those different profiles. But that's actually one of the most important inputs for us to be able to understand what the generation mix needs to do in order to meet that load curve.
Gotcha. Yeah. I mean, it seems, the demand on the system is extremely important.
Yes.
In terms of using SAM then for those simulations, can you also simulate multiple generators, multiple types of generators?
Yes. So, or I guess the question is multiple generators at a time, I'm assuming.
Correct.
So if you're interested in simulating multiple generators at a time, I would suggest you look at the PySAM programmatic wrapper. So that demonstrates the sort of quick overview that I gave earlier, matched multiple weather profiles, so multiple locations to the same plant specification. So it's essentially saying, like, if I have this sort of standard build out that I'd like to consider in multiple locations, I'd like to simulate the same thing quickly. So that code, which is described more in the README on the Git repo, the Git repository page, can cycle through a set of locations and model the same plant specification at all those locations. Mm-hmm. So I'd suggest you look at that.
Awesome. Okay, we have a couple questions about batteries. So the first is, can Sienna represent battery operation? And then the second is, with new types of batteries coming out other than lithium ion, in SAM, none of those battery models are included. Is there a way to, include those new types of battery models?
Okay, that's a great question. So Sienna Ops does have the capability of modeling storage of sort of broadly. That could include batteries, that could include other types of storage as well. I think this is getting at the fact that SAM also has battery storage modeling capabilities, but I would recommend that if you're your end goal is to do a production cost model that you not rely on SAM to generate your battery profile unless there's a specific reason for that. Like it's maybe more, I think SAM has both residential and commercial battery algorithms, but so if you're modeling a residential system, maybe it makes sense to use a combined PV and storage model in SAM. Otherwise, if it's a utility scale system that is interacting with the rest of the grid, with the market, I would suggest you use Sienna Ops directly. And Clayton, who's online, might know more about the specific standard template formulations for storage that are already available in Sienna. But part of the point of Sienna is that you can customize everything. So if you have a new technology that's not well represented by an existing formulation, then you can absolutely write a custom model for that.
Awesome. Yeah, I imagine that, with emerging technologies, it gets complicated to, be able to model everything. Here's also a great question. If we have different, solar plant capacity sizes that they want to model, is there a way to do that, at once instead of iterating over and over again the same plant design in different locations?
So, sorry, can I reiterate it back? So
Yeah.
Different plant sizes,
Mm-hmm.
but otherwise the specifications are the same.
It doesn't say, but I would assume so.
Okay, so again, this might be a application for PySAM. The way that I've showed PySAM in the demonstration is using a JSON that describes the plant specifications exported from the GUI. And that's just for ease, but you don't need to do that. You can do all of those adjustments programmatically through PySAM. And so you can define a custom model in PySAM. It's slightly more complicated though, because some of the specifications impact each other. And so you need to make those programmatic calls in a certain order. So if you're interested in doing that, I would suggest you look more at the SAM website and the developer resources there that can have some examples about how to make those calls in the correct order.
Awesome. Then also like in regards to, different energy types, different energy mix, is there a way to impose energy mix with like a different percentage of each renewable source in SAM?
In SAM. So I think this is more getting at the production cost modeling mix. So this, I think, is more in Sienna Ops. A simple way to do that is to sort of scale the capacity of different renewable generators in the system. You could also do that by, if you had a fleet of systems, just selecting a proportion for one scenario and a larger proportion for another scenario and the full proportion for an additional scenario. So I would look at either scaling capacities or disconnecting or adding additional plants in order to change the total capacity.
Great. And then we have a question here about and Clayton's typing an answer, but feel free to answer if you know. If there's an open source tool for creating demand time series, such as like adding EVs, heat pumps, etc.
That's a great question. So NREL does have some.
I was just going to jump in and say, like,
thank you. Yeah,
we do have the demand side grid research effort, tool development effort. So I'll post the link in the response to the question, but the DS grid modeling tools, this is effectively their objective. They are extremely complex and are bottoms up modeling tools, but are intended to be able to represent the evolution of electric vehicle adoption, air conditioning proliferation, and things like that, and represent the changes in load shapes that are corresponding.
Thank you, Clayton.
Thanks so much, Clayton. And then, so we just have a little bit more time. We can do a few more questions before we wrap up. Can Sienna optimize ancillary services?
Yes. So you can define whatever sort of reserve category you're interested in looking at. There are a couple standard options included, including sort of up and down reserves, as well as I'm going to forget the formulations. Clayton might be able to jump in. So there are a couple standard options already included, and those can be included in some of the template models. So we saw that in the template unit commitment, it automatically includes an up and down reserve category. We didn't optimize for that in this demonstration because we didn't have information included in the PowNet model about the system operator's reserve requirements. So the answer is yes, it can co-optimize both the energy and ancillary services.
Mm-hmm. Great. And then also with Sienna, can you do like something like a power flow?
So that is an application for Sienna Dyn, the third Sienna application that we didn't talk as much about today. But that allows you to do dynamic simulations on the same set of data that you can use for production cost modeling. So if you're interested, you could use a production cost model to identify some periods of stress and then run some dynamic simulations with Sienna Dyn on disturbances and that kind of thing.
Awesome. And then looking at the Sienna Ops application, is there capacity expansion in that application?
So not yet. I think there is some interest in that. And if you have interest in that application, please let us know. There are some existing open source capacity expansion models that are listed in yesterday's slides. So you could also give those a look.
Awesome. And then, talking about this type of model, it's a big application, you're running these, analyses, just to check, does it work on, Windows, OS X? Do you need a high performance computer? Who, has the accessibility to do this?
So I believe it's available on, this might be a question for Clayton. I'm sure it's available on Windows.
Yeah. It's cross. There are no real platform dependencies. We have examples of running it on Amazon Web Services, high performance computers, but you can run it just as easily locally on Windows, OS X, Linux, anything you want, really.
Great.
And I ran today's demonstration on my laptop.
Awesome. Yeah, I know that makes it, much more accessible, especially for this audience where a lot of people are international or may not have access to high performance computing resources. That's really, really awesome. And then looking at, Ready is obviously an excellent source for wind and solar resource data. But, if, for example, regional data isn't available through Ready, do you have any other recommendations about, where people might find other wind and solar resource data to start off their modeling and their analysis?
So that's a great question. I would also take a look, if you're looking at the NSRDB, the National Solar Radiation Database. And so that I believe includes the same locations for solar that are in Ready, but might have some others in addition. There's another resource called Solar Anywhere, and I can't recall if it's open source or proprietary. So that might be another option. For historical data, for historical forecast data, another place to look is the European Center for Medium Range Weather Forecast, ECMWF. I can't recall if they have sort of realizations of what actually happened in addition to their historical forecasts. So those are some places to start. And then also please reach out to the Ready team if you're in a location and have high interest in the data set expanding there.
Yeah, absolutely. Well, that is wonderful. I think that's kind of the end of our questions. So unless you have, any final comments or resources to share. Oh, wait, actually, just kidding. One just came in. Look at that. How timely. Sarah is asking if there is a tutorial online about how to run Sienna Ops.
Yes, so the tutorials are available in the powersystems.jl and powersimulations.jl documentation. So those links were on one of the last slides in today's sessions. We are going through sort of a resorting of where things are located. And so some of those tutorials are just being reposted in a new location, this new location now. So if you're interested in seeing more of those, I would just sort of keep an eye on those documentation pages.
Awesome. Yeah. And then obviously the recording for this session will live with the recording for yesterday's session on the event page on the Global PST, the G-PST website. So you can always come back and refer to this session and Kate's demonstration here today as well. We also have another question. We have a little bit more time. So what is the proper time resolution to capture the disturbances caused by large amounts of intermittent generation?
That's a great question. So I do want to clarify that when we talk about disturbances or contingencies, we're not necessarily talking about the variability from wind and solar. We're often talking about a generator trips off or transmission line trips off. And so that's a question for sort of a dynamic simulation to verify that the system is robust in the case of something sudden happening. When we're talking about wind and solar, large amounts of wind and solar on the grid, first of all, there's an averaging effect. And so the variability goes down as more and more sort of capacity goes online in different locations. There's sort of a smoothing effect. So it depends kind of on, it depends kind of, I guess, also on the proportion of VRE in your system and how much smoothing has happened. But I would say an hour is pretty rough for describing the variability of wind and solar, particularly when you're talking about solar. With large quantities of solar, you can have very large ramps at sunrise and sundown that are not really captured at the hourly level. So that's where a 5-minute economic dispatch is much more, has much more resolution about capturing not just the variability, but also sort of the ramping of solar. So I would suggest something sort of intra-hourly to capture variability a little more accurately.
Awesome. Well, that really does bring us pretty close to the end of our session. Kate, like I said, if there's any final comments or resources that you want to share, feel free to do so now. Otherwise, I will get us back to our final wrap up.
I think that's it. Thank you so much, everyone, for your time.
Thank you. Okay, everybody, just one moment while I share my screen. All right, thank you again so much for joining us for yesterday and today's event. We really appreciate it. For more information on the USAID-NREL Partnership, please visit nrel.gov/USAID-partnership or reach out to usaid.nrel@nrel.gov. For more information on the Global Power System Transformation Consortium, or G-PST, please visit globalpst.org or reach out to globalpst@nrel.gov. Thank you so much again to Kate Doubleday and Clayton Barrows for answering questions today and doing such a wonderful in-depth tutorial of this modeling and these tools. And we look forward to seeing you at the next session. Thank you.